record this one. Cool. All right. Well, today we have second derivatives and their graphs. So on Wednesday, we were doing first derivatives. We were sketching graphs based on the characteristics of a first derivative. So now we're going to be finding a second derivative and sketching a graph based on those characteristics. Okay, so again, bunch of definition to get through. So for this one, we deal with something called concavity. And concavity is based on your second derivative, the sign of your second derivative. So for number one, it says the graph of a function is concave up on some interval AB if the first derivative is increasing on some interval AB. So if we look at this lovely little chart down here, we have that if the second derivative is positive, this means that the first derivative is increasing, which means that the original function will be concave up. So the graph of the original function will be concave up. And what concave up looks like is graphs that look like this. They go up and to the left and up and to the right. That's what concave up is. Okay. And then the second part says the graph of a function is concave down if the first derivative is decreasing. So look at the chart again. If the second derivative is negative, this means that the first derivative is decreasing. This means that the graph of the original function will be concave down. So concave down. There we go. Okay. And now remember from last time that to determine where a function was increasing or decreasing, we took the derivative, we solved for x, we made a sign chart, and we found intervals of increase or decrease. We're going to do the same thing with the second derivative now. So now we're going to take the second derivative, we're going to set it equal to 0, we're going to solve for x and create a sign chart. So not much has changed other than having a second derivative involved. Okay, so one way to keep things simple for concavity, if the first derivative is positive, you'll be concave up. If the first derivative is if the second derivative is positive, you'll be concave up. If the second derivative is negative, you'll be concave down. Okay. All right. And do not confuse concavity with falling and rising. A graph that is concave up may be falling, rising, or both falling and rising on the interval. This would be picture number 1. So graph number 1 shows a function that is fully concave up. So it's concave up on its interval, which means that this graph is falling and rising on some interval. So to be concave up, don't confuse with being concave up as falling and rising. Okay, and the same can be said for concave down. Do not confuse concavity with rising and falling. A graph that is concave down may be rising, falling, or both falling and rising on an interval. And that would be the second picture. This graph is all concave down, and it is increasing and decreasing or falling and rising while it's concave down. So I guess it's trying to say don't get confused with the terminology. If you see concave down, don't assume that it's just all falling. Concave down could be rising and falling. All right, so that's what concavity is. Concavity is based on the second derivative. Now, in order to find concavity, we need to find something special called inflection points. So remember, first derivatives had critical numbers. Second derivatives have something called inflection point. It's where concavity changes. So an inflection point is a point in the graph where you can go from concave up to concave down or concave down to concave up. So you have an inflection point if concavity changes. If you do not change concavity, then it is not an inflection point. So for concavity to change at a point, the second derivative must change sign. So you must go from positive, negative, or negative to positive in order to have an inflection point. Okay, and then a theorem for inflection points. If the point C f of C is an inflection point of the original function, then C is a partition number for the second derivative. So we saw partition numbers last time. Critical numbers were partition numbers, and now inflection points will be partition numbers. And all that means is that we're going to create a sign chart and break up the number line. We are going to partition the number line. Okay, and it would only be an inflection point and a partition number if the sign changes, if concavity changes. Okay. Important, partition numbers for the second derivatives are only candidates for inflection points. The function f must be defined at x equals c. So the function f must be defined at the inflection point, and the second derivative must change sign at the inflection point in order for the graph to be an inflection point at this value of c. So again, I mean, I've been saying it. So in order to be an inflection point, the sign must change. Concavity must change. Okay, so all that definition is done. Let's go ahead and work out an example. Given a function, we want to find the intervals on where we are concave up and concave down, and then we want to find the inflection points, and then we want to sketch the graph based on everything we found. So in order to find inflection points and intervals of concavity, we must find the second derivative first. So that's what step A I labeled. A, find the second derivative. Okay, so given this function above, negative x to the fourth plus 28x cubed minus 28x plus 3, we're going to start with step A and find the second derivative. So first, we must find the first derivative to get to the second derivative. So the first derivative is going to be negative 4x cubed plus whatever 28 times 3 is. (84x squared minus 28). There's our first derivative. And then get our second derivative as negative 12x squared plus 84 times 2. What's that? 168. 168x. There's our second derivative. Okay. And what we're going to do now in step B, we're going to set this derivative equal to 0. We're going to solve for x, and then we're going to create a sign chart, and we're going to find points of inflection. So much fun. So B, h double prime of x equals 0. We take negative 12x squared plus 168x equal to 0. And I don't know if 12 comes out of that nicely. Let's see. Probably not. Oh, it does. Nice. So I can take a negative 12x out, and this will leave me with x minus 14 equal to 0. Okay. Set both terms equal to 0, and we'll get x equals 0 and x equals 14. Okay. So these are not yet inflection points because we have to test them on the number line on our sign chart. So these are possible inflection points. Possible inflection points, or we could say pips. Okay. So B is almost done. We still need to create the sign chart. So that's next. Where's my room? I still have room here. Okay. So I'll draw my sign chart. I'll say sign chart. Let's see. There's negative infinity, positive infinity. Plot our pips. So 0 and 14. And just like last time, create intervals. Negative infinity to 0, 0 to 14, and 14 to infinity. And then we pick test numbers. Three intervals, three test numbers. So 1, 2, 3. And then from negative infinity to 0, we can pick -1. From 0 to 14, I'll just pick 1. From 14 to infinity, I'll pick 15. And now, to note this, this is a sign chart for the second derivative. So plug these into your second derivative. Okay. So you'll have h double prime of -1, h double prime of 1, and h double prime of 15. And Desmos, here we come. Oh, where's my second derivative at? Right there. -12x squared plus 168x. Table feature. And then type in my numbers there. -1, 1, and 15. There we go. And once again, we don't care about the number. We only care about the sign. So when we plug in -1, we get -180. So I'm just going to put a minus there. When we plug in 1, we get +156. And when we plug in 15, we get -180. Okay. So what this means, let's see, zoom in a little bit, is that on the interval, -infinity to 0, this means that the second derivative, no matter what number we pick, will always be negative, which means that if the second derivative is negative, the first derivative is decreasing, which means the original function will be concave down. So this will be concave down. Concave down. And then from 0 to 14, we picked 1, which gave us a positive output. So this means that no matter what number we pick from 0 to 14, the output will always be positive, which means that if the second derivative is positive, the first derivative is increasing, which means the original function will be concave up. And then last is negative, which means we'll be concave down. Okay. Maybe we could draw what concavity looks like for there. That'd be down, and then up, and then down. There we go. Okay. Which means what is it? I think B is almost done. Maybe I put them together. Let's see. What did I put for my instructions? So we created a sign chart. We found the possible inflection. We plotted the impossible inflection points. We just found our concavity. So let's go ahead and determine the intervals of concavity and the inflection points. Okay, so we'll call this step C. All right, so C. We are concave up on the interval 0 to 14. And then we are concave down on the intervals -infinity to 0 and 14 to infinity. So there's our concavity. But now we need to see if our possible inflection points are actually inflection points. Does the sign change at these inflection points? So we can call this D, inflection points. Okay, so we look at the first inflection point at the sign chart above. And just zoom in on that. There we go. There we go. Okay, so we look at the first inflection point up there, the sign chart at 0. We see that we go from concave down to concave up. We also see that we go from negative to positive. So we see that the sign has changed. This means that since the sign has changed, since concavity has changed, 0 is an actual inflection point. So we say X equals 0 is an inflection point, which means that we look at the next inflection point, 14, and we go from positive to negative, and we go from concave up to concave down. Since sign has changed, since concavity has changed, this means that 14 is also an inflection point. Okay, but since we're graphing this, we now need to find the actual points of inflection. So we know that they are inflection points, but we need to know where are they on the graph. So since we are graphing the original function, we take these points and plug them into the original function, h of x. So plug into h of x. So we'll have h of 0, h of 14, and I need the original function, and Desmos. Get rid of that. Come back here to my original function. There you are. Okay. So this is going to be negative x to the 4th plus 28 x cubed minus 28x plus 3. All right. And then I'm going to plug in my inflection points. 0, which is there already, and 14. Oh boy, 38,000. That's nice. So we get 0 gives me 3, and 14 gives me 38,027. Oh man. And these are the points of inflection. So these would create the points 0, 3, and 14 and 3, 8, 0, 2, 7. Okay. Well then, let's graph. We're going to graph based on our sign chart and our points of inflection. Yes, the perfect graph is over here on the left side. Of course, to see that other inflection point, I would need to make this y-axis go up to 39,000. There we go. And my x-axis needs to go to 15. Is that gonna work? Let's see. Or I'll put 20. Why not? Hey, there we go. Now that's the perfect graph. Okay. So first thing I'm gonna do is plot my points 0, 3, and 14,038. 14 and 38,000. Oh goodness. Okay. So 0, 3 is going to be right here. What are we on? Good. 0, 3, too big. Okay. And then 14. So let's just say that these are gonna go by 2s. So 0, 2, 4, 6, 8, 10, 12, 14. And let's just pretend that up here is going to be our 38,000. Like you said, it's just a sketch, so it doesn't have to be perfect. All we have to do is finish this by graphing using the concavity from our sign chart, which is right there. Let's see. Zoom, zoom. And we know that, so here's how we graph using concavity. We know that from negative infinity to 0, the function's concave down. So that means that we'll start at our point of 0, 3, and this is what concave down looks like. And then, so all of this is concave down. And then from 0 to 14, we are concave up. So this will change direction. This is what concave up looks like. So that's concave up. And then from 14 to infinity, we are back to being concave down. So we turn around and head back down. And that's concave down. There we go. Almost as cool looking as this one.
How did we verify that the possible inflection points actually were inflection points?
By the sign chart. Remember that in order for them to be inflection points, the sign has to change and concavity has to change.
Okay, that's right. All right, thank you.
Good. Good question. All right. And that was graphing using concavity. Any questions on that before moving on? So just about the same process as last class.
Last class with the test numbers, we plugged them into the original function, and here we're plugging them into the second derivative.
Well, no. So for last class, it was all about the first derivative. So when we made that sign chart, the test numbers were plugged into the first derivative.
Oh, okay.
This time, the test numbers are plugged into the second derivative.
Cool.
But now on the next example, we're going to be doing the first derivative. We're going to be doing everything we did on Wednesday. And then the next step, we'll be doing everything we just learned now and putting that all together to graph this function. And this is called the graphing strategy, which is on the next page. So in step 2 is everything we learned on Wednesday. So everything we learned on Wednesday has been placed into one single step. So if you missed Wednesday, well, here you go. One step is the whole lesson that we covered. Okay, so this is called curve sketching, and we use the graphing strategy to analyze the function. So the first thing we're going to do in step 1 is find the domain of this function and the X and Y intercepts. So this is no calculus involved. This is just basic algebra. Domain, X and Y intercepts. And for you guys get the easy curve sketching because you will always be given polynomials. And that's what we'll start with. We'll start with domain. And here, since this is a polynomial function, the domain of all polynomial functions is always negative infinity to infinity. So this is easy points for you guys. You won't get anything other than a polynomial. And I'll state here because f of x is a polynomial. Okay. Which means that we can move on to finding the x-intercept. To find an x-intercept, you let y, or f of x, equals 0. So we take this function and we set it equal to 0, and we solve for x. So here I can probably take a 3x squared out, and that'll leave me with x squared minus 6 equal to 0, right? 3x to the 4th, negative 18x squared. Good. Set both of these terms equal to 0. You'd have 3x squared equal to 0, x squared minus 6 equal to 0. Then if you divide it by 3 on the first one, you get x squared equal to 0, square root both sides, and you'd still get x equals 0. Then over here, move that 6 over, square root both sides, and you'd get x equals plus or minus the square root of 6. Okay, since we're going to be plotting this, we might as well change the square root of 6 into a decimal number. I'll just use my calculator that I have at home, and this is about 2.45. Okay, these are the x-intercepts. All right. Also, I'll put them in coordinate form. So this means that my x-intercepts are going to be 0, 0, square root 6, 0, and negative square root 6, and 0. Okay, and then last is the y-intercept, which is always the easiest because you let x equal 0. And this means you plug 0 in for every x. You'd get f of 0 equals 3 times 0 to the 4th minus 18 times 0 squared. And all of that just gives you 0. Okay. I think on my math lab, when it wants the y-intercept, it just has y equals. So I think you'll just put y equals 0. It doesn't want the coordinate point. I think the same for the x-intercepts. But I put the coordinate point so we know that we can plot it when we graph it. Okay. So your answers for my math lab will probably be this for your Y-intercept, and will probably be these for your X-intercepts. It'll be X equals, it's not going to ask for an actual coordinate. Okay. So that's domain and intercepts. We know how to do that stuff. Okay. Next is step 2, where we do everything we did on Wednesday. So we're going to take the first derivative, set it equal to 0, solve for X, create a sign chart, find intervals of increase and decrease, and find maximums and minimums. Ugh. All right. So let's go ahead and take that first derivative before I scroll down more. So we're going to say f prime of x, and from the function above, we should get 12x cubed minus 36x. Okay, there's the first derivative. All right, and now we set it equal to 0. And solve for x. So here I can factor out a 12x. That'll leave me with x squared minus 4. And then I can factor more, because x squared minus 4 is a difference of squares. So that factors to x plus 2, x minus 2. And then I set all 3 terms equal to 0, and I'll get x equals 0, x equals -2, and x equals 2. All right. These are all considered my critical numbers. And now we plot them on a sign chart. Yeehaw. So -2, 0, and 2. Create our intervals next. So I'm going to move over. Let me zoom in. Intervals. -infinity, -2, -2, 0, 0, 2, and 2 to infinity. Okay, and then test numbers. 4 intervals, 4 test numbers. So 1, 2, 3, and 4. And from -infinity to -2, I'll pick -3. -2 to 0, I'll pick -1. 0 to 2, 1. 2 to infinity, 3. Come on, laptop, keep up. Now, this is a sign chart for the first derivative. So plug into first derivative. So f prime of -3, f prime of -1, f prime of 1, and f prime of 3. Okay, now, once again, Desmos here to help us. I just need that first derivative. 12x cubed minus 36x. Yes, okay. And then table, come back here. Plug in my numbers. Here we go. -3, -1, -1, 1, and 3. And again, we don't care about the number, only the sign. So I see negative, positive, negative, positive. Which means if I go to my sign chart here, if we're negative from negative infinity to -2, this means that the original function is decreasing. And then from -2 to 0, we're positive. So this means we're increasing. And then negative again, decrease, and then positive again, increase. Okay. Put this away. Okay. So now we can answer where we are increasing and decreasing on. So increase and decrease. So we increase on the intervals -2 to 0 and 2 to infinity. And then we decrease on the intervals -infinity to -2. And 0 to 2. So there's our intervals of increase and decrease. And then the last thing we want to find are the max and minimums, which means we have to look at the sign chart and say, and look at the intervals of increase or decrease. And remember that, well, first we're going to look at the critical number of x equals -2. So we'll say x equals -2. We see that we decrease and then we increase. So we decrease and then increase. This means that -2 will be a local minimum. You decrease and then you increase. So -2 is a local min. And then we look at 0 and we increase, decrease, which means 0 is going to be a local max. And then we look at 2. We decrease, increase, which means again that 2 is going to be a local min. Okay. And now you want to find the exact location so we can graph them. So you must plug all of these in to the original function. Okay, so once again, Desmos to help me out. Let me find the original function, which is up there, 3x to the 4th minus 18x squared. Table, and come back here. I plug in -2, which is there for me already. 0 and 2, they're all on that chart for me already. So -2 gives me -24, 0 gives me 0, and 2 gives me -24. 4. These are the locations of all your maxes and minimums. So these would be the points -2, -24, 0, 0, 2, -24. Minimum, maximum, minimum. Okay. So that's everything we did on Wednesday into one single step. Whew. Any questions so far? All right. Now we move on to what we learned today. Step 3. Find concavity and inflection points. So now we're going to take the second derivative, set it equal to 0, create another sign chart, and find intervals of concavity and see if our possible inflection points are inflection points. So before leaving there, I need that second derivative. So f double prime of x is going to give me 36x squared minus 36. 36x squared minus 36. Right? 3 times 12. Yes. Okay. Now moving on. Set this equal to 0. Just see how far I can zoom in. So f double prime of x equals 0. 36x squared minus 36 equal to 0. I can factor out a 36. And that'll give me x squared minus 1 equal to 0. And then I can factor. I have a difference of squares. That's x plus 1, x minus 1 equal to 0. And we set all 3 of these equal to 0, although one of them is not going to matter because you get 36 equal to 0, which doesn't make sense. So that's not anything. And then here you'll get x equals -1 and x equals 1. So these are going to be our possible inflection points, our pips. Okay. Sign chart time. There's negative infinity. There's infinity. Here's -1. Here's 1. All right. Zoom in. Intervals. Negative infinity to -1. -1 to 1. 1 to infinity. Test numbers. 3 intervals, 3 test numbers. X equals, x equals, x equals. Negative infinity to -1, we pick -2. -1 to 1, 0. And 1 to infinity, we'll pick 2. Now, this is a sign chart for the second derivative. So plug into f double prime of x. F double prime of 2. All right, there we go. Desmos. Need that second derivative typed in. 36x squared minus 36. Change that to a table. And over here, -2's in there already. And then 0 and 2 are in there already. Cool. -2. Oh yeah. So again, we only care about the sign. So here at -2, we are positive. At 0, we're negative. And then at 2, we are positive. All right, perfect. Okay. So if we're positive from -infinity to -1, this means we're going to be concave up. And then from -1 to 1, we're negative, which means we're concave down. And then from 1 to infinity, we're positive. So we're concave up, which means, there we go. Okay. So we can find our intervals of concavity. Concave up, concave down. And we are up on the intervals -infinity to -1 and 1 to infinity. And we're only concave down on the interval -1 to 1. Okay. And now we need inflection points. So I'll put that here. All right. So we look at our first possible inflection point of -1, and we look to see if the sign changed and or if concavity changed. So we see that we go from plus to minus, which verifies it's already an inflection point. Or you look at the concavity and we went from up to down. So that also verifies that x equals -1 is an inflection point, which means that when you look at 1, you go negative to positive. That's all we need. Or you go concave down to concave up. Concavity changed, so x equals 1 is also an inflection point. And now you want to find these points of inflection, so we must plug these into the original function. Almost there. Back to Desmos. Now I still have the original function in there. So at -1, I get -15. And at 1, hey, I get -15. So these are my points of inflection, which make the points -1, -15, and 1, -15. Oh, man. All right. So we have all the information we need now to graph this function. Oh boy. Okay. Let's see. We'll start to make our graph appropriate. Let's look at all our x values starting at the very first step. So I have x values at 0 and square root of 6 or 2.45. And then I look at my next step and I have x values at 2 and -2. And then I look at my last step and I have x values at 1 and -1. So we'll leave the x-axis completely alone. And then I'll look at my y values. On the first step, I have a y value of 0. Perfect. On the next step, I have y values at -24. So that means we're going to have to adjust to go to -24. And on the third step, I have y values of -15. So this means we're going to have to adjust again that y-axis for -15. Okay. Does this thing even look like it goes down to -15? Where are we? Unless I messed this up somehow. I hope not. When I plug those into the original function. -2 and -24. Why? Oh, okay, never mind. Yes, we're good. And then -1 and -15. Is that at a 15? It sure is. Okay. So now we're good. I'll probably just have to adjust this. Let me see. My x-axis should go from -5 to 5. And my y-axis should go down just to -25. Why not? And end at, we'll just say 25. Let's see what that looks like. Perfect. Okay, that's much better. Okay, so let's go ahead and plot the x-intercepts first, 0 and 2.45. So let's look at this and label 0, 1, 2, 3, -1, -2, -3, and then I have 0 and 2.45 and -2.45. There's my intercepts. And then let's graph our minimums, max and mins, 0, 0, and -2, -24, 2, and -24. So that means that I'm going to have to adjust this by 3s. That's fine. So here's -3, and then 6, 9, 12, 15, 18, 21, 24, negative, 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 negative. And I said 0, 0, which is there already. 2 and -24, which is right here. -2 and -24, which is right there. There's my maxes and my minimums. I'll label them, why not? Min, min, max. And last thing to graph is the actual inflection points. 1, -15, -1, -15. So back here, 1, -15, and -1, -15. Okay. Whew. Oh boy. All right. So now graph the rest of this by your sign chart for the second derivative, which I'm looking at above in small print. It says from -infinity to -1, we are concave up. So this means we look like this. All of that is concave up. And then from -1 to 1, we're concave down. So we would go like that. All of that's concave down. And then from 1 to infinity, we're concave up. And there it is. All that work to draw W. Concave up, concave up, concave down. And there it is, y'all. That is called curve sketching. Now imagine if you got another function other than a polynomial.
That looks terrible.
Life would be rough. Rougher than this one, I guess, already. All right. I mean, it's not too bad though, because this is pretty repetitive, is it not?
Yeah.
It's true.
It's pretty repetitive. And step 2 and step 3 are almost the same, except one's the first derivative and the other's a second derivative. But any questions on this before moving on? All right. All right, last one. Thank goodness. All right, example 3. Zoom in, there we go. The marketing research department of a computer company used a large city to test market the firm's new laptop. The department found that the relationship between price P dollars per unit and the demand X units per week was given approximately by P equals 1296 minus 0.12x squared on the domain of 0 to 80. So weekly revenue can be approximated by R of X equals X times P. This is the revenue function. So they take X, multiply by the P value above, 1296 minus 0.12x squared, giving us a revenue function of 1296x minus 0.12x cubed on the domain 0 to 80. Okay. First step says find the local extrema for the revenue function. Okay, so to find local extrema means we're going to take the first derivative, set it equal to X, create the sign chart, all that fun stuff. So that's what we're going to get started. See, repetition is key. So for A, you find the first derivative of this one, and the derivative of 1296x is 1296 minus the derivative of 0.12x cubed is going to give me 0.36x squared. Okay, and then set your derivative equal to 0 and solve for x. So here we can use the square root method on this one. You'll get 1296, move that x over, you'll get positive 36x squared. Then divide by 0.36. And I'll just my calculator here. 1296 divide 0.36, we get, hey, that's a nice number. 3600 equal to x squared. Okay, now you're solving for x. So we'll square root both sides, and the square root of 3600 should give me plus or minus 60 equal to x. Okay, but now we're talking about business. We're talking about a real life application. So what number can we not keep?
Negative 60.
Negative 60. Good. So we only stay with the positive 60. Which means now we plot this on a sign chart. And actually, we have limits. What two numbers are we still told to stay between?
0 and 80.
0 and 80, which means we only plot 60 here. So this means that my intervals are 0 to 60 and 60 to 80. And then we pick test numbers, which means that from 0 to 60, I'll pick 1. From 60 to 80, I'll pick 61. plug into revenue, the derivative for revenue. So R prime of 1 and R prime of 61. And just looking at this first derivative over here, if I plug in 1, we're going to get a positive number. So that's going to be positive, which means that if I plug in 61 to this function up here, we should get a negative. So go ahead and check that if you want, but for time's sake, we'll believe in the pattern. So that'll be plus and minus, which means that we're only talking about local extrema, max and mins here. So we only talk about increase, decrease. So this means that we increase, decrease, which means all this wanted us to do was find the what number makes the max. So since this increases and decreases, we can say that X equals 60, since it increases and it decreases, X equals 60 is a local maximum. There you go. All right, so X equals 60 would be a local max. If it wanted you to find the actual value, the point at 60, you would do what we did on the last problems. You would take this value and plug it into the actual revenue function. But I don't think it's asking us to do that because we're not graphing it. Okay. Next is concavity, which means we're going to take the second derivative and solve for X. So since my first derivative is up there, my second derivative is going to be the derivative of 1296 is 0, and the derivative of negative 0.36x squared is negative 0.72x. All right. So there's our second derivative. Set it equal to 0. Solve for X. Well, if you divide by 0.72, you're going to get X equals 0. There's our pip. Oh yeah, up there was our critical number. There's our pip. And now, can we even plot it on our restriction 0 to 80?
No.
Not really, but it belongs on there. So this means that our sign chart just goes from 0 to 80. And all we want to know is that where are we concave up and where are we concave down? So for this sign chart, we just pick our test number on this interval 0 to 80. So here, I'll just write everything again. Interval is 0 to 80. And then my test number that I'll pick from 0 to 80, I'm just going to pick 1. And now we take this test number and plug it into the second derivative. So you'll get R double prime of 1. Well, if I plug 1 into here, the answer is going to be positive or negative?
Negative.
Negative, which means that from 0 to 80, this whole function will be concave down. And that's all I want to know. What interval are you concave up or down? So will this function ever be concave up?
No.
No.
I missed the part. How'd you get to only 0 to 80?
Because remember, that's the restrictions they gave us.
Oh, okay.
We can only be in those intervals. And they're telling us that our inflection point is 0. So this means we can only use that interval of 0 to 80 to pick a test number.
Oh, okay.
Yeah. So we'll say concave down on the interval, oops, 0 to 80. And this means we are never concave up. And this kind of makes sense on why it's concave down, because if you were to graph this function, well, it would look like this. Here's 0, here's 80. It would look like this. And right here is where I have my local max when x is 60. All right. And that's second derivatives and their graphs. Oof. We are done.